Welcome back, everyone, to AI Talks with Chris and Nita, ready for another deep dive.
Always ready.
All right, today we are going to be taking apart activation functions. And we really are going to break this down for people who are totally new to the concept. So think of it this way. You know how a light switch can be on or off?
Yeah.
It's kind of like that with activation functions. They're like the switches in artificial neural networks.
Right.
They decide whether a neuron should fire or not.
That's a really good analogy. And the key here is that these activation functions introduce what we call non-linearity into the model, which is a fancy way of saying they let neural networks learn these really complex patterns.
Okay, so non-linearity. Can we maybe unpack that a little bit for people who are hearing that for the first time?
Sure. So imagine you are trying to predict something simple, like how much a house costs, based on how big it is. You might think, oh, bigger house always means a higher price. That's a linear relationship, like a straight line on a graph.
Yeah.
But the real world is messy. House prices, they depend on way more than just size. Right?
Well, of course.
Like the location, number of bedrooms, even when the house was built. All those things matter. Mm-hmm. Those relationships are a lot more complex. Yeah. And you can't just represent them with a straight line.
Right.
So that's where non-linearity comes in.
So you're saying without activation functions, the neural network would be stuck in that oversimplified straight line world, unable to really deal with the complexity of real problems.
Exactly. Without activation functions, even a deep neural network would basically be limited to making these super basic predictions.
Right.
It would really struggle to capture the nuances, the complexities of real data, especially for things like image recognition or natural language processing.
That makes sense. And actually, our source material specifically calls out ReLU as an example of an activation function. That introduces this really critical non-linearity. And it talks about something called a non-linear decision boundary.
Yeah.
Can you help us picture what that actually looks like?
Sure. Imagine you're teaching a computer to tell the difference between cats and dogs in pictures. A linear decision boundary would be like drawing a straight line on a graph to try and separate all the cat images from the dog images.
I see.
But what if you've got these really fluffy cats that kind of look like dogs? That straight line wouldn't be able to separate them very well.
Right.
But ReLU, with its non-linear decision boundary, lets the network draw this more complex, curvy line to separate those tricky cases much better.
It's like giving the network more flexibility.
Exactly. It's like giving it the flexibility to learn the subtle differences.
Yeah.
Even between fluffy cats and dogs.
That's a great analogy. I love that. So we need these nonlinear activation functions to really get these neural networks learning complex patterns. And I understand there are actually different types of these functions, each with its own strengths and weaknesses. Can you maybe walk us through some of the most common ones?
Of course. So let's start with the most basic one, the linear activation function. It's essentially a straight line, meaning the output is directly proportional to the input.
But wait, didn't we just say neural networks need nonlinearity? Why would we ever use a linear activation function?
You are absolutely right. If we just used linear functions everywhere, it would totally defeat the purpose of having this deep network.
Yeah.
But linear activation functions, they do have their uses, mainly at the very end, in the output layer of the network, for certain types of problems.
It's more about using them strategically rather than as the main building blocks of the network.
Precisely. Now let's get to the more interesting stuff, the nonlinear activation functions. One of the most well-known is the sigmoid function, famous for its S-shaped curve.
Oh yeah, I remember seeing that S-shaped curve.
Yeah.
Back in my intro to AI class, what makes the sigmoid function so useful?
So the sigmoid function takes any input, and it squashes the output to be between 0 and 1.
Okay.
And this is really useful when you're dealing with tasks like binary classification, where you want the network to predict the probability of something, being either one thing or the other.
So if we were building a spam filter, sigmoid would be a good choice because it could give us a probability score for whether an email is spam or not.
Exactly. Now, another common function is tan, short for hyperbolic tangent. It's similar to sigmoid, but its output ranges from monocle 1 to 1, making it zeo-centered.
Okay.
And this can actually lead to faster and more stable training, especially when used in the hidden layers of the network.
Interesting. So it's all about picking the right tool for the job.
That's a great way to put it. And now let's talk about a rock star in the world of activation functions, the ReLU, short for a rectified linear unit.
I've heard ReLU is super popular these days. What makes it so special?
ReLU is all about simplicity and efficiency. It's computationally inexpensive.
Yeah.
Because it just outputs the input if it's positive and 0 otherwise. It's basically like a filter that only lets positive values through.
I see. Now, our source material also mentions this concept of sparsity as a key advantage of ReLU. Can you explain what that means and why it's a good thing?
Sure. So sparsity means that with ReLU, only a subset of the neurons are actually activated at any given time.
Okay.
And this not only makes the network faster, but it also helps to prevent something called overfitting.
Overfitting.
Yeah, overfitting is when the model learns the training data too well, and then it doesn't perform very well on new, unseen data.
Right.
It's kind of like studying for a test by just memorizing the answers instead of actually understanding the concepts.
So ReLU helps the network to generalize better.
Exactly.
That's really cool. So are there other nonlinear activation functions out there besides these 3?
Yeah, there are a couple more mentioned in our source material, softmax and soft plus. Softmax is really interesting. It's specifically for those multi-class classification problems.
Multi-class classification. So instead of just like cats and dogs, it could classify images into like different breeds of dogs.
Exactly. Imagine you're trying to predict who's going to win a race with like multiple runners.
Okay.
Softmax takes those raw outputs from the neural network and it turns them into probabilities, so each runner gets assigned a score, representing how likely they are to win.
So it's not just about picking a winner, it's about understanding the chances of each contestant.
Precisely. Now, Soft Plus is a bit more specialized. It's kind of like ReLU in that it always outputs a positive value,
Right.
but it's smoother and differentiable everywhere, which can be helpful in certain cases, like training certain types of generative models or in reinforcement learning.
Okay, so we've got this whole toolbox of activation functions, but our source material also talks about the impact of activation functions on model performance. What are some of the key things to think about when you're choosing the right function for a specific task?
Yeah, that's really important. The choice of activation function can actually make a big difference in how well your neural network learns and performs.
So what kind of factors come into play there?
Well, one thing is convergence speed. Some functions, like ReLU, let the network learn faster and get to a good solution more quickly during training. Others, like sigmoid and ton, they can slow things down a bit, especially in deep networks with many layers.
So it's like some functions are speed demons and others take their time.
Yeah, that's a fun way to put it. Another important factor is gradient flow.
Oh yeah, I remember that term from earlier. But I'm still not quite sure what it means.
Right, so imagine you're training a neural network. It's kind of like teaching a dog a new trick. You give the dog feedback, right? You tell it what it did well and what it needs to improve.
Yeah.
Gradient flow is like that feedback loop in a neural network. It's how information flows backwards through the network during training, so the model can adjust its internal parameters based on the errors it makes.
So smooth gradient flow means the network is learning effectively.
Exactly. And some activation functions, like ReLU, they're great at making sure that feedback loop stays strong and stable.
Okay.
Others, like sigmoid and ton, they can sometimes have problems where the gradients either vanish or explode, making it hard for the network to learn, especially in those deeper layers.
So it's almost like they create traffic jams
Oh.
in that feedback loop.
Yeah, that's a great analogy. Another thing to consider is the complexity of the task. For relatively simple problems, ReLU might be all you need. But for tougher tasks, like image classification with lots of categories, you might need something more sophisticated, like softmax.
So there's no one-size-fits-all solution.
Nope. It really depends on what you're trying to do.
And I guess even experienced AI folks don't always know which activation function is best right away.
Right. It often takes some experimentation. You try different options, evaluate their performance, and fine-tune the model until you get good results.
That makes sense. Now, our source material also mentions the computational cost of these different activation functions. Can you talk a little bit more about that?
Sure. Some activation functions need more computing power than others. ReLU, with its simplicity, is really efficient, which is great when speed matters. But others, like sigmoid and ton, might need a bit more processing power.
So you've got to balance finding the right function, but making sure it doesn't slow the whole system down.
Exactly. It's a trade-off between performance and efficiency.
This has been so helpful. We've really learned a lot about activation functions, their purpose, the different types, and how to choose the right one. But before we wrap up this deep dive, I'm curious, have you ever run into any surprising challenges when working with activation functions in your own projects?
Oh yeah, definitely. You know, it's funny. even these small choices about activation functions can really have these big ripple effects on the whole model. I remember working on this image recognition project, and we were using a sigmoid function in one of the layers. Seemed like a reasonable choice at the time, but the network was really struggling to learn.
Oh, so it was like hitting a wall.
Yeah, exactly. We tried tweaking all sorts of things, like the learning rate, the architecture, nothing seemed to help.
Wow.
And then we just decided to try swapping out the sigmoid for ReLU in that layer.
Okay.
And suddenly everything just clicked. The network started training way faster. The accuracy went way up. It was a real aha moment, showing just how important these little decisions about activation functions can be.
That's amazing.
Yeah.
So for our listeners out there who want to learn more, what resources or advice would you recommend?
Well, if you want to get into the theory, there are some great deep learning textbooks out there. One that comes to mind is Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Corville.
Okay.
It really gets into the math behind activation functions.
Yeah, and I'm sure for the more hands-on learners, there are lots of online tutorials and courses that can teach you how to implement these functions using frameworks like TensorFlow or PyTorch.
Oh yeah, for sure. And don't be afraid to just experiment. The best way to really get it is to try things out yourself, play with different options, and see what happens.
So to all the aspiring AI enthusiasts out there, don't be afraid to get your hands dirty and explore.
Yeah, you never know. You might just make the next big breakthrough in deep learning.
That's a great point. Even if you don't invent a new activation function, just learning about them will help you build better AI systems. Well, this has been a fantastic deep dive. We've learned so much about activation functions, what they are, the different types, and how to choose the right one.
Yeah, it's been a pleasure talking about this. Hopefully everyone listening now has a better understanding of these crucial parts of neural networks.
And who knows, maybe one day you'll be designing your own, pushing the boundaries of what AI can do. Until next time, happy learning, everyone.